5.2 The kinetic theory of gases. Let's begin. Gas and its molecules. In this chapter, we will continue our study of the behavior of gases. We will apply the kinetic theory of gases to explain the relationship between gas temperature, volume, pressure, and the mass of gas. 1. Random motion of gas molecules. According to kinetic theory, a gas is regarded as a large number of molecules in random motion traveling at high speed. In this chapter, we will use this kinetic theory to explain the relationship between gas volume, pressure, and its absolute temperature. Experiment 5D. Observing the motion of smoke particles. This experiment was introduced to you in Secondary 1. In the original experiment, pollen grains were found to be in random motion under the microscope. Scientists thought that the motion is due to the living pollen grains themselves. Then boiled pollen grains were used, and the scientists can still observe the random motion. And now smoke particles are used, and still they are in random motion. How do the scientists explain that random motion?
We will observe the random motion of gas molecules using a smoke cell and a microscope. Inject a little smoke into the smoke cell. Place the smoke cell under the microscope. Adjust the objective lens until the smoke particles in the cell are clearly observed. Then, observe the particles through the microscope. The smoke particles appear as bright spots as shown. How do they move? Can you explain their motion using the kinetic theory of gas?
The smoke particles move about along zigzag paths because they are constantly bombarded by a lot of tiny air molecules moving randomly from all directions. But the bombardments from all directions are not equal in number, and so it is moved a bit to different directions continuously. Such experimental result is an indirect proof that gas consists of a large number of tiny molecules in random, high-speed motion. 2. Assumptions about ideal gas. The kinetic theory has the following assumptions. 1. Identical molecules. 2. Random motion. 3. Large number. 4. Tiny molecules and large separation. 5. Negligible collision time. 6. Elastic collisions. 7. Negligible intermolecular force. These approximations are good even for real gas when the gas is at high temperature and low pressure. In other words, real gases are ideal at high temperature and low pressure, since macroscopically they satisfy the general gas law, and microscopically they satisfy all the above assumptions.